We can start.
We can start.
Welcome to our secret seminar. Okay, I'm very happy. Many people. So I think the tea time idea seems to be successful. Thank you. Today's speaker, Victor Yanke from GIST. So he will talk about quantum chaos.
Okay, so thank you very much for the introduction. Thank you very much for the opportunity to give this talk here, for the invitation. So I'm mostly going to be talking about a particular measure of quantum chaos, which is a particular probe of quantum chaos, which is known as OTOC. So OTOC is an out-of-time order correlator. I will introduce it precisely later, but this is an outline of my presentation. I will make like a very brief introduction, then I will introduce the concept of OTOCs, and I will tell you how these objects behave in chaotic systems, and I'll try to give you some sort of like intuitive picture of why they behave the way they do in chaotic systems. So this is going to be like more like intuitive approach, like try to create some sort of physical picture of what's going on, rather than boring you with technical details. Then I'll explain a little bit how to compute this in the context of ADS-CFT. These correlators will have like a very interesting representation in the dual graphed picture. And finally, I will discuss some comparisons between classical and quantum Lyapunov exponents. So this, sorry? Oh, thank you. Let's save this. Okay. Can you see the pointer? Okay, good. Okay, so yeah, so recently this OTOCs, this is an abbreviation for out-of-time order correlators. It's basically a 4-point function which is out-of-time order. That's it. And they have been recognized as useful tools to diagnose quantum chaos, especially many-body quantum chaos. So this will be useful for like spin chains or like field theories at large n, for example. And besides characterizing quantum chaos, these OTOCs also have other applications, like they can be used to diagnose traversability of traversable wormholes. This has a dual interpretation in terms of teleportation protocols. This is mostly my area of research recently, but OTOCs also have some connections with diffusion phenomena. And yeah, so I'm just mentioning here a few applications of OTOCs, but I guess people think about OTOCs most as a way to characterize quantum chaos. And they have an interesting dual description in ADS-CFT. And in this dual description, you can understand their universal properties as being related to properties of black holes. This is a very nice description. So I'll try to give you an overview of these recent developments, which started roughly like 10 years ago. Okay, so let's start from classical chaos. Classical chaos is something that is relatively well understood, and there are different possible ways to characterize classical chaos, and perhaps a very popular way of defining it is by this idea of sensitive dependence on initial conditions. So basically, let's say you have some classical system, and your system has some trajectory in phase space. But if you change your initial condition a little bit, you get a different trajectory, which differs from the initial one. And the idea is that in a chaotic system, a very small change in the initial condition leads to some big changes in the future. So for instance, the distance between initially nearby trajectories increases exponentially with time. And this is characterized by the so-called Lyapunov exponent, okay? And you can see like you can compute this for any point in phase space, but usually a more precise definition, people usually define this Lyapunov exponent by performing some sort of average in phase space. Okay, so this is like
I won't catch it.
Yeah, sure.
So phase space is essential. So some people, I think, they just took the configuration space and distance can be larger than initial time.
I think you can do. I think you can do that, but I think it's important to have phase space because usually the phase space is kind of mixed. You have like some region with chaotic orbits, other regions with classical orbits, like regular orbits. So to get a sense of the global properties of the system, people usually average over phase space. But you can also talk about like local properties of phase space. So to consider like a possible quantum generalization of this, what people usually do, like, okay, so you want to measure this sensitivity on initial conditions. Basically, you want to see how much your trajectory changes as you change the initial condition. So it's very natural to consider this derivative. And this derivative can be written in terms of this Poisson bracket. And once you write this in terms of this Poisson bracket, it's immediately clear how to consider the quantum version of this. You just replace Poisson bracket by a commutator. Okay? So as I told you before, usually people perform some averages in phase space. So what we want to do is to consider the average of this object in some quantum state. That's the basic idea. However, this object has some particular phase that might. So if you just consider the average of this, you might get some cancellations. So to avoid phase cancellations, people usually define the square of this quantity. This is more useful. And take the expectation value in some particular quantum state. So this was first proposed by Larkin and Obishnikov in the 60s, but people didn't pay too much attention to this. But it was recently like revived by people from ADS-CFT community. People basically rediscovered this sort of independently in the context of black holes.
So do you know why they consider that? I think that is about the superconductivity paper.
Yeah.
So then why they care about this kind of quantity? You know?
Yeah, I think Larkin is still alive, and he's a guy that studies quantum chaos. And the point is that this quantity, within some time scale, it kind of correctly reproduces the classical behavior. The classical equations of motion are kind of valid within some average in some. If you take the expectation value of the classical equations of motion, they are valid in the quantum case, but only up to some time scale, which is the Ehrenfest time scale. So I think they had this type of motivation in mind, some sort of semi-classical description, but I don't know precisely the motivation. But this is like Larkin has many papers about quantum chaos. Yes.
Yeah.
So
Q partial QT over partial Q equal
yes.
coordinate Q.
Yeah.
There's no P.
You could So but that's the definition of Poisson bracket. Like let's see if I remember here. Okay. If you have like Poisson bracket of A and B, those guys are quantities. Let's say A and B. A is like a function of phase space coordinates, and B is also a function of phase space coordinates. If I remember correctly, like the Poisson bracket between A and B, it's something like this. Please correct me if I'm writing something.
Q and P are independent variable.
I think yes. A and B. But of course, like if you don't like this Poisson story, you can just directly compute this. You want to know how much a later measurement of P affects Q. But in general, like in phase space, you define some distance, which involves like Q square and P square, something like that. So more generally, people just generalize this concept to generic operators, W and V. So if you have like a spin chain, this could be just some Pauli matrix in some particular site, for example. And they consider, in general, people consider these guys to be permission operators, and they use these two to diagnose chaos. Just the commutator square. So the idea here is that you just want to know how much early measurement of V affects W, this kind of story. but it's simply a commutator. So let me tell you now what type of behavior you expect from this commutator square in a chaotic system, okay? And I'll try to explain intuitively why they behave in some particular way. Yeah, so some people refer to this as OTOC, but in the original definition, people refer to this as double commutator. And this guy has a piece, which is out of time order, which is the actual OTOC. But the literature about the subject is kind of not like super, the terminology is not super consistent, like between different authors. So some people refer to this commutator as OTOC. But
Crazy question. So,
yes.
Are there any constraints for choice of operators?
Yeah. So normally you try to come up with like natural choices. For instance, in a spin chain, maybe you want like some Pauli matrix at some particular site. Or in holography, people usually take like single trace operators. But of course, like if you put the Hamiltonian here, you just get the time derivative of the other. So the Hamiltonian is not a good choice of operator. But apart from that, I think the statement is that this should be able to diagnose chaos for almost any operator.
But should not be some symmetry.
Yeah, so that's a good question. Like if you consider conserved density, conserved currents here, I think you get a different behavior. But the people have not studied this much yet. But that's a very good question.
And one question. So that beta important? If we choose the zero temperature.
Yeah, beta is important. Like usually people consider this in a thermal state. Having in mind applications with black holes, they are dual to some thermal state. So if you put zero temperature, you usually get no chaotic behavior. Like,
so your commutation relation is not actually not equal time commutation.
Yeah, that's true. That's true.
So actually common delta function t minus t should be zero actually to get the non-trivial answer in commutation rate.
Yeah, so let me get to this point here. Like, what happens if you take like this commutation relation different times is that you could just for simplicity, I will take operators which are both Hermitian and unitary. So the square of these operators are 1. But this is not essential. But this would be the case, for example, for a spin chain. So any Pauli matrix, some particular size square will be equal to 1. But if you just open this commutator, you get the first piece, which here is a constant, but in general, it will be some time order correlation function. But because you're considering commutators at different times, you get also a second contribution, which is this 4-point function.
Yeah, yes, in the previous page.
Yeah.
So where is the delta function?
Delta.
Yeah, so equal time. Yeah, that is not the equal
No, yeah, I mean, like if it's an equal time, you get just some delta, Kronecker delta, that's your point, right? Yeah, so here there is no Kronecker delta because it's different times.
So can you define consistently non-equal time commutation?
No, I think the point is that you don't get the simple result. Like if they are equal time, you get just 1, right? Or like H bar. But if they are different times, you don't get like a simple result. You get something that will kind of measure the chaotic properties of your system if you take the expectation. But this will be like a non-trivial correlation function. That's my point.
So what is the origin of the non-trivial correlation between non-equal time?
I'll try to explain that. Okay. Yeah. So basically, let me make first the statement. The statement is that for a chaotic system, and for almost any operators, V and W, you will get this behavior. This commutator square will increase initially. This is supposed to resemble like this divergence of classical trajectories in phase space in systems in which that have a semi-classical limit. But then this guy saturates. And so one C is related to the OTOC by this formula. So this basically implies that the OTOC starts at 1 and decays to 0. So my statement here is that in chaotic systems, the double commutator and the OTOC will behave this way. And one behavior implies the other. So sometimes it's useful to use C, sometimes it's useful to use the OTOC, but that's the statement that, and now I'm gonna try to give you some sort of like intuitive idea of what's going on here, okay? And the point is that this is sort of universal. You get this for almost any choice of operators. So of course you should compare this with what happens in non-chaotic systems. And in non-chaotic systems, you have a distinct behavior, and it's basically non-universal. So it depends on the operators. For chaotic systems, for almost any operators, you get this result. And if the system is not chaotic, it's like integrable, you can get a result that doesn't saturate, maybe oscillates, but it depends on the operators. It's basically non-universal. So the working definition of chaos here is that you get some universal properties because your Hamiltonian is complicated enough, okay? So let me try to explain a little bit why this behavior is related to chaos. So there are several ways to understand this in a sort of like physical way, but in practice, of course, you have to do the calculation to get these results, but let me try to give you some sort of intuition.
So you are saying in integrable system, there's no universal behavior or OTOC?
Yeah, I mean, like, for instance, if you take some integrable model, depending on the choice of operators, you get just a constant or something that oscillates. But if the system is chaotic, you get this sort of universal behavior. So that's one possible way to think about chaos. You get some universal behavior because the Hamiltonian is so complicated that some sort of like statistical description applies and you get some sort of universal thing.
So if you beta varialize, then what happens?
Yeah, so that's a very good question. For instance, if you have some temperature which is high enough, you get this universal behavior because the thermal bath is sort of introducing chaos in the system. However, if you go to zero temperature, then this is no longer true in general, and you get something that is non-universal and will be related probably to the properties of the ground state. So you need the temperature to introduce chaos in general. Yeah, sure.
Then the nature of chaos is related to the thermal or quantum.
Yeah, so it's kind of the thermal thing is kind of important, but it's also a property of the Hamiltonian. I'll give you some examples that hopefully will clarify this. I mean, like, you need the Hamiltonian to be complicated, but you also need the to consider a thermal state, at least when you think about OTOCs. There are other measures of chaos which are sort of like state dependent. They only depend on the spectrum of the system. So this is kind of a problem of OTOCs, I guess. It kind of mixes like the state with the Hamiltonian. Okay, so yeah, so perhaps a good way to understand why this commutator grows is that you initially, like, you consider a commutator between V and W, and if you consider that these are operators kind of separated in the system, and normally if the system has some notion of locality, these operators will commute, right? However, as you consider the time evolution of this operator, the operator gets more and more complicated as you consider time evolution. So what happens in practice is that this operator kind of grows in the space of degrees of freedom. And after some time, it manages to have a non-zero commutator, even with operators which are far away. So for instance, in a spin chain, if your spin chain is chaotic, as you commute your operator with the Hamiltonian, you get more and more terms, which if you have a operator which initially acts only on the first side of the chain, as you consider these nested commutators, this operator effectively grows. It starts to act in more and more sides, and eventually manages to affect all the degrees of freedom. So perhaps it's also useful to think about this as some sort of infection, for example, some epidemiological model. The operator initially, only this operator is infected, but eventually it infects all the system. And it manages to have a non-zero commutator, even with the operator which is far away. So this happens in chaotic systems, of course. If you have like a very simple integrable system, maybe this doesn't really it grows to some extent, but maybe it doesn't affect all the degrees of freedom of the system. So this provides some sort of intuitive picture of why this C grows. Okay. And classically, if you compute this double commutator, classically it just grows exponentially forever, for example. But in quantum mechanics, there is some saturation, which is related to quantum mechanical effects, interference, this kind of stuff. And as I told you before, this implies that OTOCs vanish. So let me now try to explain what's the physics behind the vanishing of OTOCs, which is kind of it's not easy to see why OTOC vanishes from this picture, but so let's use another one. So I think this picture kind of helps to understand in what way are OTOCs measuring chaos. And the basic idea is as follows. So let's say you have a very special initial configuration for your system, but as you evolve the system in time, usually you get a more typical configuration, right? So if you, anyways, like you can get this just applying this time evolution operator. But if you apply a time reversal operator, this basically goes back to the initial configuration. It's like just watching a movie and rewinding. Okay. So that's the basic idea, right? By applying this time evolution operator backwards, you recover the initial configuration. However, let's imagine that after evolving the system and getting this more typical configuration, you change a little bit the position of one of the particles. If you try to get back to the initial configuration, you basically don't recover the initial configuration, because this small perturbation kind of propagates to, it has an effect on everybody, and you simply do not recover the initial configuration. And from the mathematical point of view, is that this W operator inhibits the cancellation between time forward operator and time backwards operator, okay? So basically, because these guys do not commute with the Hamiltonian, you no longer get this cancellation, because there is an operator between these two time evolution operators. So that's the main idea of OTOCs. I'll try to be a bit more clear about that. But basically, the OTOC is measuring this sort of effect. You evolve the system in time, you apply some operator, and then you evolve the system backwards in time, and you don't recover the initial configuration. That's maybe the main message of this talk, to understand like OTOCs from the quantum mechanical point of view.
Question?
Sure.
Yeah, it's a simple question. So naively, classically, CT corresponds to scale of exponential lambda t, right? And then it's average, right?
Can you ask your question again?
Right. So CT is
CT.
yeah. CT is order of h bar square, right?
Yeah, that's true.
Okay, then the basic question is, I mean, classically, CT never saturates and then grows infinitely at the infinite time.
Right.
Right. But then how the quantum mechanical effect with the small h bar square can overcome so that you have a saturation?
Yeah, so basically, I think this is related to the Ehrenfest theorem. Ehrenfest theorem, it's basically saying that classical equations of motion are valid in quantum mechanics if you take the expectation value of the operators. But this is only valid up to some time scale, which is the so-called Ehrenfest time. So here, the time scale is the so-called scrambling time. And after this, the usual understanding of this, which is also due to Larkin or Vishnikov, is that quantum effects kick in and lead to desaturation. because the classical description breaks down. And I think if you have like trajectories in phase space, maybe you can start with some wave packets, which are very, let's say they are very localized, and they sort of simulate this movement of particles. But after some time scales, the wave function sort of spreads. So this classical picture totally breaks down. So that's the usual understanding for this saturation.
I see. Okay, thank you.
No problem. Yeah, so to be a bit more precise, the way to better understand the vanishing of OTOCs, usually what people do, they consider OTOC as some sort of amplitude. So basically you consider one state in which you act with two operators on your, let's say, thermal state beta, and you have like this sort of amplitude. So here actually I'm thinking about the purification of a thermal state, some sort of like thermal field double state, for example, and I'm representing this by just a line. And the basic idea is that the line represents the thermal state, let's say. So this is not a precise argument, it's just an intuitive picture, just to be clear. So the basic idea is that you start with this thermal state, and you apply this operator V. So basically this produces a state which is slightly different from the thermal state, and it's represented by this line with a bump, okay? So this is just a representation of this state. If you evolve the system either forward or backwards in time, usually the system thermalizes. The perturbation basically disappears, it melts into the thermal path, and you get something that is very similar to the initial thermal state. So here I'm evolving the system backwards in time by applying some time evolution operator with the flipped sign for the Hamiltonian, and I get this sort of like thermal state. So if I evolve the system forwards in time again, this perturbation rematerializes. Basically, what I'm saying you is the same thing that I was saying here. I have some initial configuration, I go forwards and backwards in time, and I recover the initial configuration. So this is what's happening here on the left side. However, if before I go back to the future, I apply some perturbation, I no longer recover the initial state. I recover something that is similar to the thermal state. So that's the basic statement. You start with some special initial configuration, you go back to the past, you change something in the past, and you no longer recover the initial configuration in the future. So this is the in part of the OTOC. Now, if you look at the out part of the OTOC, you start with this thermal state, you go back to the past, you apply some operator, you go back to the future, the operator thermalizes, and then in the end, you apply the operator V0. And when you do this set of operations, you get something that resembles your initial state. So basically what the OTOC is measuring is how much your initial state is similar to your final state, how much your out state is, which is kind of similar to the initial state. It's similar to this in state. So yeah, so basically, since you get like a different state, it's somewhat clear that they are not the same, and they have like not a perfect overlap. And it results that it turns out that in chaotic system, this overlap is very small. Basically, but the basic effect that I'm trying to explain here is basically this one. But I'm going back to the past in that slide. If you have some special configuration, you go to the past, you change something. As you go back to the future, you don't recover the initial condition. So that's the main effect, the main physics behind the vanishing of OTOCs in chaotic systems. Is that so? At this point, is sometimes not super clear. I'm not sure if I explained well, but please ask questions if this is too confusing. This is not a rigorous argument, it's just some sort of mental picture of these things. I'll try to be more precise in a moment. But like, yeah, please just remember, like, I have some, so you can think about this. In the past, I have a system which is sort of fine-tuned to produce a bump at t equals 0. I have this the system defined here by the set of operations. And if I just evolve the system in time, the system at time 0 displays a bump, okay? However, if I change a little bit the system in the past, I do not recover the bump. That's the main physics. And this will have a realization in black hole physics. That I'll try to make this point clear in the black hole scenario. So now we are going to, yeah, sure.
I'm asking same question again. So I think if we start some integrable spin chain,
Yes.
and if we add some integrability breaking term,
Yeah.
for example, magnetic field or
Yeah.
whatever, then I think in your heuristic explanation, non-zero temperature seems not important. So maybe we can investigate some, for example, if we study rebel statistics,
Yeah.
we can find out some Poisson or Wigner ice.
Yeah, that's true.
Without temperature.
Without temperature.
What happens? So in OTOC,
Yeah, so that's a good point. Like when you talk about level space statistics, it only depends on the spectrum. It doesn't depend on the state. You take the Hamiltonian, you compute the spectrum, and you have the level space statistics. In my experience, OTOCs only work at some finite temperature. Maybe they also work for some other states, but if you put OTOCs at 0 temperature, then you're basically taking these expectation values in the ground state of the system. And the ground state is usually kind of universal. Not universal, it's kind of system dependent. So I think that's the reason, like if you compute stuff at the ground state, you get like something that is not universal. It will depend on the particular ground state. I'm not sure. Does that answer more or less your question?
okay, I know that's good answer. Okay.
Okay, so we are going to be discussing that in the context of ADS-CFT correspondence, in which basically you have a gravity theory that lives in asymptotically ADS space, and this is due to some boundary theory, which is usually a CFT, and this CFT lives at the boundary of ADS. As I told you, OTOCs work well if you consider thermal states. So we are going to consider a thermal CFT, a CFT of finite temperature. And if you have the CFT of finite temperature, the dual gravitational description will be given in terms of ADS black hole geometry. And the black hole the special properties of the black hole will be responsible for the universal properties of OTOCs. Okay, so before I discuss OTOCs in ADS-CFT, let me discuss a little bit the physics of, for example, thermalization. So for each operator in your CFT, there is a corresponding field in ADS, right? And let's say you have here a thermal state, which is again represented by just this line. And if you apply some operator, you create some sort of bump. But if you wait long enough, this bump sort of melts into the thermal bath. That is just the statement that the system thermalizes, right? So this is just a representation of thermalization in a picture. In the dual gravitational description, what happens when you apply this operator in the boundary is that you create some sort of field fluctuation in the bulk. And this field fluctuation changes the geometry here in the bulk. And this deviates from the thermal state. If you compute anything like a 2-point function here, this will change the geometry, and you will get the 2-point function in the presence of this bulk field, not the 2-point function, for example, for a thermal state. However, this field fluctuation eventually falls into the black hole, and as it falls into the black hole, you have a configuration in which this field fluctuation no longer affects much the geometry. So if you compute something here, like a 2-point function, for example, you will get a result which will be very similar to the result you would get just in the thermal system without this perturbation. So the process of thermalization in the boundary theory has a dual description in the ADS side, let's say, in terms of a particle that falls towards the black hole. And once the particle crosses the horizon, like the system thermalized, return to thermal equilibrium.
You mean bump means perturbation?
Yeah, some perturbation. By bump, I mean just,
Perturbation of the boundary.
yes.
Then what is the corresponding perturbation in the black hole side?
Yeah, so basically, for each operator in the CFT, there is a corresponding field in ADS. And basically, yeah, once you, if you just apply your operator on the thermal system,
Which breaks the unitarity, which breaks the perturbation breaks the unitarity of quantum mechanics.
No. I mean, like I could just turn on a source for this operator.
Because in the presence of a perturbation, so the state cannot be retrieved from the perturbation. The entropy is increasing.
Yeah, I think that's one of the big mysteries. Like, how does, like in the classical system, I think people understand well how thermalization occurs. But in quantum mechanics, due to unitarity, it's kind of tricky to understand how.
In your picture, actually box model, so the final state cannot be purification cannot be retrieved after adding some perturbation.
Okay.
So I'd like to know what is the origin of perturbation. So externally imposed some operator.
Yeah, I could just apply some operator, turn on a source for some operator, some external operator. Yeah, this.
But in the black hole side, I'm wondering what is the external.
Yeah, it's just like in the ADS CFT, it's like the same geometry, but you have like some, let's say, some scalar field in the geometry propagating in the geometry.
Scalar field.
Yeah, for example, yeah. I'm not sure if I understand your question, but that's how the ADS CFT dictionary works. Like if you turn on a source for some operator, on the dual picture, you have like some scalar fields, some classical scalar fields in the geometry.
So I'm confusing. So in the spirit of ADS CFT, unitarity should be preserved, maintained.
No, but I don't think this breaks unitarity.
But in your previous pages, so actually in the box picture,
Yeah.
actually the purification does not occur.
No, sorry. The problem is that you apply some operator.
Yeah, here.
Yeah.
So
So it's not like you break.
perturbation.
Yeah.
Yeah, so purification cannot be retrieved after time evolution.
No, yeah, but that is just the statement that this doesn't commute with the Hamiltonian. Like, I mean, like if this were just an identity operator, I would have like something. I would return this initial state, but it's just because I'm introducing this.
I think the entropy is always increasing.
Yeah, but you're going forwards and backwards in time. So here, like you go back.
Entropy is not the same.
No, because you're going backward and forwards in
It
time.
means the entropy is increasing.
No, it could because you're going backwards in time. It could like decrease, for example.
Decrease in this case, decrease.
No, I don't. I'm not talking about entropy here. I think here entropy continues to increase. Yeah, it's
random.
Yeah. But anyways, let me circle back to your question later, perhaps. So basically, in the black hole side, not sure how much time I have. Yeah, so let me try to discuss the vanishing of OTOCs in the black hole side. This is the last sort of intuitive picture. Then I'll start describing this with some more details. But the initial idea is that as I told you before, I had some thermal state, which is sort of fine-tuned to produce some fluctuation at some time. Let's say this is time 0. So I have a state which looks thermal, and then I evolve the system in time. It produces some bump at t equals 0. What's the dual description of this in terms of black holes? This is described in terms of a particle which is initially near the horizon, but it manages to escape to the boundary. So you might imagine some particle which is highly energetic here, and somehow it has energy to escape to the asymptotic region. So this fluctuation in the dual picture would be some particle that reaches the boundary, then falls towards the black hole again. Of course, this is supposed to be kind of similar to this picture here. I have something that resembles a thermal state, but as I evolve the system in times, it spontaneously produces a bump, okay? By definition here.
So second, that is not the, you mean, that is not the time evolution, just a backward.
Yeah.
Just a backward.
Yeah,
In the
yeah.
sense that this is not the time evolution.
It could be like either forwards or backwards in
Yeah.
time.
Yeah, forward and backward,
Yeah, precisely.
not the,
Not just time evolution. Yeah, precisely. I think now I understand your question. So in the black hole, I have like so this is my boundary here. So the gray part here is supposed to be the black hole. So what happens if I perturb the system in the asymptotic past? If I perturb the system, for instance, applying some operator here, this creates a particle which then falls towards the black hole. And what happens is that usually as a particle falls towards the black hole, it gets blue shifted. And in fact, the energy increases exponentially. So if the particle falls for a very long time, it gets so much blue shifted that increases the horizon of the black hole a little bit. So in general, I will refer to this black dotted line as a V particle. So the V particle will be affected by the presence of the W particle. And in general, it will sort of reach the boundary, but with some time delay, which in gravitational scattering, people refer to this time delay as a Shapiro time delay. But here I'm representing the situation where the back reaction of W is so big that the black hole increases and captures this particle. So the particle never materializes here. So basically, you go back to the past and you do a small change in the past, and again, you don't recover the initial configuration because of a small change in the past. So this is the book picture for the vanishing of OTOC. And you can think about this in terms of, for example, a science fiction movie like Back to the Future. If you go back to the past, you change something. As you go back to the future, you don't recover the initial configuration. You get something different. Okay, so let's now be more precise. So essentially, what I'm showing you here is that there is a collision between these two particles in the book. And this collision essentially characterizes this OTOC here. And in practice, what you do is that when you want to compute a boundary OTOC using ADS-CFT, you basically consider some scattering between these two particles, okay? And since one of these particles is escaping from the black hole, to reach the boundary, it needs to have like a lot of energy, and the other particle, VW particle, is falling towards the black hole, so it has a lot of energy because it gets blue shifted. This is actually a high energy scattering. And this simplifies a little bit the calculation. So the punchline of this talk is that OTOCs are related to a high energy collision that takes place close to the black hole horizon. And like the special properties of the black hole horizon will give rise to universal behavior of OTOCs. But this is basically the punchline. So to be a bit more precise, how do you do this? So usually the setup that is convenient to do this type of calculation is the setup of a two-sided black hole. So basically, if you have like some black hole geometry, you can always define Kruskal coordinates and maximally extend the geometry. And we are going to be considering asymptotically ADS geometries. And this is the corresponding Penrose diagrams. So in this geometry, you have two exterior regions. And you have like a future interior, a past interior. And these lines here represent the black hole horizons. And this has the interpretation, if you consider like a constant time slice here in the middle, this has the interpretation of wormhole geometry. So this is a two-sided black hole. You have basically two black holes connected by a wormhole. And in ADS-CFT, this two-sided black hole has a dual description in terms of a purification of your thermal state. which is given in terms of this thermofield double state. So I'm sorry if this is not super clear, but so this is the type of setup that it's usually convenient for computing OTOCs. And what one normally does is that, as I told you before, one divides the OTOC into parts, and you consider this part as an in state and this part as an out state. And in the in state, the particles are heading to collide. In the out state, the particles are leaving the collision region. And you basically compute this considering this is scattering. And these particles in general, they have some back reaction on the geometry. So if you have some initial geometry, which has some line element described by S0 square, you get some additional contributions to the geometry, which are related to the presence of these particles. In general, this back reaction is actually simple. It can be modeled by shockwave geometries. And so we are interested in computing this boundary 4-point function, and it can be described on the gravity side as also a 4-point function between bulk operators, and they are connected to the boundary by propagators. And it turns out, since this is a high energy collision, you can actually use the so-called iconal approximation, in which this 4-point function in the book is basically given by a phase. And this phase, basically you consider this type of interactions, like you consider the two particles are exchanging a graviton or two gravitons, basically consider a sum of ladder diagrams. And of course, like, as you think about this 4-point function, in principle, you have many contributions for this in the book, right? You can have many type of vertices, and it might be, in general, very tricky to compute this 4-point function. But the essential point here is that the gravitational interaction dominates, because this is a high energy collision. As you consider a high energy collision, this gravitational interaction is much stronger than any other type of interaction. So you basically disregard other type of interactions and consider only the leading term, which is given by these graviton exchanges, by the sum of ladder diagrams.
Only ladder diagram.
Only ladder diagrams, yeah.
And can you resum from Schwinger-Dyson?
Yeah, so the ladder diagrams, you can in general resum, and you basically get some exponent of one loop or one 3-level result. So this is a major simplification, and also, so this happens in the so-called Regge limit, in which the collision has a lot of energy. In the center of mass energy is very big and fixed impact parameter. But outside of this limit, I don't think anybody knows how to do this calculation. But the point is, the OTOC is modeled as this collision between these particles. And of course, this interaction between the particles is in general very complicated, but the gravitational interaction dominates and gives rise to the universal behavior of OTOCs. So basically what you need to do here, you need these propagators and you need this phase shift. And the OTOC will be basically controlled by these two ingredients. And so let me tell you what you find when you do this calculation. What happens is that this phase shift has this form. It's basically the energy in the center of mass square. And usually it decreases exponentially as the particles are separated in space. But this energy in the center of mass, it increases exponentially with time. And this is the origin of the Lyapunov exponent in the gravity picture.
What is mu? Mu?
It's a parameter that comes from the geometry. But I'll explain more about that in a moment. But here, once you introduce these shock waves, the shock wave has a spatial profile, and mu is determined by metric functions, basically, at the horizon. So basically, the OTOC behaves like that in some region. Like I told you, the OTOC basically decreases. So in this region of decrease, there is a region in which it behaves exponentially. And so this result is for this particular window. And you see that the non-trivial part of the OTOC, it's proportional to G Newton. And if you use the ADS-CFT dictionary, from the point of view of the boundary, this would be like 1/n squared. It has this exponential dependence with t, and this was sort of like identified as the quantum version of the Lyapunov exponent, but it also has some spatial profile, which I'll talk about in a moment. And yeah, so this calculation was first done by Stanford and Shanker in almost 10 years ago, and Kitaev recognized this sort of behavior as some sort of like a quantum version of the Lyapunov exponent. Because yeah, so if you compute, for example, the C, the square commutator, it will be basically proportional to this part without the 1. So there is also some additional ingredient here, which is the butterfly velocity. I'll talk more about the butterfly velocity in a moment.
1/Gn is entropy of the system.
Yeah, I mean, like, kind of. I mean, like, G Newton in ADS-CFT, in the most studied example, this will be related to 1/n squared. So it's kind of like number of degrees of freedom per point in space.
1/n squared.
1/n squared. So it will be kind of related to entropy. Entropy scales with n squared. Yeah, so expanding time here it's written like this. 1/G Newton, I can write like this, but you can also write the scrambling time roughly like as black hole entropy, for example. You're precisely right. Anyways, so yeah, that's the result. And yeah, so basically you get the Lyapunov exponent, which is given by 2π times the temperature. And it turns out that people try to compute this also in string theory. So they consider stringy corrections to this picture instead of classical gravity. You have like strings. And what they notice is that these stringy corrections only reduce this Lyapunov exponent. So this was kind of suggestive. And eventually they realized that this is actually the maximal possible value that this Lyapunov exponent can have. So this was shown, oh, sorry, let me skip this slide. So this is the so-called chaos bound. It was derived by Valdesena, Shanker, and Stanford in 2015. And basically they noticed that, also previously I wrote the Lyapunov exponent as 2π times t, but if you include all the units, you should also include this Boltzmann constant and this h bar. But people normally take these two numbers as 1 in high energy community, hep-th community. But anyways, actually, so basically, they basically show that using some analytic properties of 4-point functions and also some large n factorization, they were able to show that the Lyapunov exponent is basically bounded by the temperature. And this is not shown in the context of ADS-CFT. It's actually a general statement. It only requires the use of large n factorization, analytic properties of correlation functions. So this is a statement that it's more general than ADS-CFT. It extends outside of the scope of ADS-CFT. However, since black holes or systems which are dual to black holes, they always saturate this bound. People say that black holes are maximally chaotic. Because if you have a system and it's dual to a black hole, the Lyapunov exponent is automatically given by 2πt. And this is the maximum possible value. So this sort of shows that holographic systems are very special because they are always maximally chaotic. So this is important because it provides you with a way to find holographic systems. If you have a system, you believe the system is holographic, and you believe the system is due to a black hole, then you can just check, you can compute the OTOC and check if it's maximal. If it's not maximal, probably the system is not due to a black hole.
When fetch rate, what is the choice of V and W?
For almost any choice. However, there is some evidence that the bound is a bit different, for instance, if you have a rotating black hole. But if you have a rotating black hole, actually, you don't have usually I'm considering the bound was derived by a thermal density matrix, which is something like this. But if you have a rotating black hole, the dual description is usually understood in terms of a different type of density matrix. Some sort of like generalized Gibbs ensemble. So the bound was derived by this type of state. And there is a work by Idrina Halder, which tries to derive this bound for a state like this, some generalized Gibbs ensemble. And there is a bit of a controversy here regarding the sign below here. Mark Mezai has some different sign in the denominator. But there is like quite strong evidence that the bound changes, for instance, in rotating black holes. But if you're not considering a rotating black hole, you get this NSS bound people.
So does saturation value of MSS bound depend on your gravity model? For example, if we consider modified gravity model.
No, okay. I mean, like, it doesn't imply that the system is holographic, but it's sort of like a necessary condition, I would say. But maybe you can come up with a model which saturates the bound, but it's not holographic. But if it's holographic, then it must saturate the bound. That's how I understand. So anyways, I don't know how much time we have. So I better finish in 5 minutes or
10 minutes.
10 minutes? Okay.
Formally 5 minutes. But
Okay, so there is also like this so-called butterfly speed, which I mentioned before. So if you consider local operators, this OTOC also has a spatial profile. So usually you consider correlation functions are supposed to be non-zero inside the light cone, but this butterfly speed defines a somewhat smaller cone inside which this commutator is non-zero. And like, so the Lyapunov exponent regards scrambling in each point in space, and the butterfly speed concerns like how scrambling progresses in space. Okay, so maybe I don't want to talk too much about that. Just to finish, I would like to say that this sort of exponential growth doesn't happen always. There are certain conditions for exponential growth. And usually you need to have some sort of semi-classical limit. So usually you compute this commutator and you get some small number here, some small prefactor. So in semi-classical system, this small prefactor is just h bar square, for example. But in ADS-CFT, this small prefactor is given by 1 over n squared, for example. Okay, so traditionally, the quantum chaos community study quantum chaos in semi-classical limit. Basically, they consider like one particle system, but in the semi-classical limit. But OTOCs and ADS-CFT, they are sort of like studying quantum chaos in large n systems. So they are exploring this region here, which were not previously explored, at least not very much, by people from quantum chaos community. I took this picture from a paper by these authors. These guys are experts in quantum chaos from the traditional point of view of studying quantum chaos. They're not from hep-th community. And they made this observation that OTOCs are sort of useful to characterize the so-called many-body quantum chaos. But if you have a system that do not have a classical limit, then usually you don't get this exponential growth. So for instance, in spin chains, so this is a spin chain. By choosing the parameters, I can make a transition from chaotic to integrable. but I never get some exponential growth, even if the system is chaotic. Actually, the early time behavior is very similar, but OTOCs can still distinguish chaotic from integrable because in chaotic systems, the OTOCs decay to 0 at late times, but in the integrable case, they just also keep they keep oscillating. So I don't have much time to talk about that. To finish, I would like to just compare a little bit the definition of classical Lyapunov exponent and compare a little bit with the quantum Lyapunov exponent. So in the classical case, people usually consider some distance in phase space, and they take the log of this distance. So if this distance increases exponentially, they take this log to extract this exponent. And usually after taking the log, they perform the average in phase space to define this classical Lyapunov exponent. But in the quantum Lyapunov exponent, what people actually do, like if you take this quantum Lyapunov exponent and goes to the classical limit, actually you don't really recover the classical Lyapunov exponent. And this happens because the order in which you take the average and the log are different. People in the quantum Lyapunov exponent, you first perform some average in phase space, and then you take the log. And so because of that, in general, the classical Lyapunov exponent and the quantum Lyapunov exponent are in general different. And one problem with the quantum Lyapunov exponent defining it this way is that it's kind of overly sensitive to small regions which are chaotic in phase space. So if you have a system which is basically integrable, but it has only some special points in the phase diagram which are chaotic, OTOCs are kind of overly sensitive to these chaotic regions. And they might mistake a system. They might, according to OTOCs, you might think that the system is chaotic, but it's actually integrable. And this is basically related to the order in which you take the average in phase space and the logarithm. So this is a problem for OTOCs. And it's explained here. So this is the so-called saddle point scrambling. OTOCs were shown to mistake quantize an integrable system for chaotic ones in the presence of saddle points. So this is basically a false positive for OTOC. The OTOC says the system is chaotic, but in fact it isn't. And there's a proposal which was done earlier this year by Tuning. And you can fix this problem of OTOCs by defining the so-called logarithmic OTOCs, in which you consider the commutator square, you take the log, and then you perform the quantum average. And this guy argues that this way of defining the quantum Lyapunov exponent kind of matches precisely to the classical version of the Lyapunov exponent. Yeah, so I think that's pretty much all I have to say. So just to finish, I would like to say that the holographic description of quantum chaos has provided new insights into the inner works of gauge-grafted duality. And in particular, I think people are really interested in OTOCs because they allow us to find simple models for holography. For instance, the SYK model was basically proposed having in mind the properties of OTOCs. Yeah, so basically, this also provides insights which are outside the scope of holography. For instance, the proposal of quantum Lyapunov exponent, chaos bound, and also provides a tool to diagnose chaos in QFTs at large n. So I guess this is all I have to say. Thank you very much for your attention. Oh yeah, sure.
You have to explain us that string effects will use the level.
That's right.
How can you understand essence from the boundary viewpoint?
Okay. So let's see. That's a difficult question. I think, okay. From the boundary point of view, I'm not sure if I have a very good picture, but what happens is that, like, maybe I can try to explain this in the book, and hopefully, as I explain this in the book, the boundary picture becomes more clear. But in the book, usually, I think this phase shift, which controls the Lyapunov exponent, is basically given by, it's basically S to J minus 1, where S here is basically the energy in the center of mass squared. And so J here is you have like the V particle, the W particle, and they are exchanging a particle of spin J, okay? So in the book, what happens is that this particle is actually the graviton, so J equals 2. And you get this phase shift, which is basically proportional to S. However, if you include strings in the book, what happens is that this phase shift will be given by a sum in J of terms like this, right? And if you have just a finite number of higher spin fields, this would lead to a violation of the chaos bound. Because this here basically implies lambda will be 2 pi t J minus 1. So in string theory, if you consider just a finite numbers of higher spin currents, usually you violate this bound. But just a finite number of higher spin currents is not allowed by causality reasons. So in string theory, what happens is that you sum over J for higher string loads, but this sum is infinite. And it turns out that after summing all the terms, you get something that reduces this guy. So you're basically summing higher spin currents, but infinitely many higher spin currents. So I guess from the CFT point of view, if you don't have these string states, the dominant contribution comes from the exchange of a stress energy tensor in the OPE conformal block expansion. So I guess like in the CFT, you have like some sort of like higher spin currents or something like that. But I unfortunately don't have a good understanding of this. What these string states represent from the point of view of the boundary CFT. Maybe you know better. Sorry, I don't have a very good understanding of how the dictionary applies under the presence of stringy corrections. Stringy corrections should be dual to 1/n corrections in the boundary, I think. Sorry, I don't have a good understanding, but that's a good question.
Another question.
Sure.
Can you explain the holographic aspects of the quantum current recurrence time in your setup?
Oh, yeah, sorry, I don't have a good picture about the Poincare. Yeah, so in the classical setup, you can use a Poincare recurrence or Poincare section.
Recurrence time scale.
Recurrence time. Okay. In the ADS CFT. You mean like the system should eventually, after a very long time scale, eventually should go back? Yeah,
I asked about the holographic picture of that.
Okay. I don't have a understanding of how this comes about in holography. But I have to say that in the case of OTOCs, the time scales are much shorter. I think Poincare recurrence time, maybe it's like E to the S.
Yeah.
So at this time scale, I don't have a good answer, sorry.
Professor,
Take 26.
Oh, sure.
Explain a little bit more for the right-hand side of the figure.
Oh, sorry, I had to rush about this part. Yeah.
I guess you skipped this.
Yeah. So basically, so you have a quantized spin chain, right? And this has no classical counterpart. And depending on the choice of parameters here, you can get either chaotic or integrable system. But how do you define chaotic or integrable system in a system that is totally fully quantum mechanical, has no classical analog? what people usually do, I'm not sure if there's so much light here. Maybe can I?
The green light. No, the green
bulb. Okay, thank you. So yeah, basically, if you choose, for example, hx to be -1, hz to be 0, this system becomes integrable, and you can make a change of variables and solve it, have analytic solutions and everything. And in this case, okay, so however, if you choose, for example, this choice of parameters, the system is not solvable anymore. And what people usually do to characterize chaos at the quantum level, they look at level spacing statistics. So they basically list all the energy eigenvalues of the system and look at the distance between adjacent eigenvalues. Okay. So they call this level spacing statistics. So it's basically EI plus 1 minus EI. There are some technical stuff here, but essentially it's the difference between neighbor eigenvalues. And if you plot a histogram of this distance, what you get is that if the system is integrable, you get something that resembles like a Poisson distribution, in which this basically behaves exponentially. And in this case, when the system is integrable, you get what is called level clustering. Many energy eigenvalues are close to each other, and they are completely uncorrelated. However, if you consider the chaotic case, what you get is the so-called level repulsion, and you get this sort of linear distribution, which is written here. And basically, you don't get the histogram is 0 as you go to 0, meaning that you don't have like much overlap of energy eigenlevels. They are kind of separated from each other. So this is the most, let's say, standard definition of quantum chaos, and only depends on the spectrum of the system. So for this spin chain, you can use this sort of characterization to say that this particular choice of parameter leads to an integrable model, and this particular choice of parameter leads to a chaotic model. Now you can look at OTOCs to see if you get a consistent picture. And in the case of OTOCs, if you take the chaotic case, what you get is an OTOC that decays to 0 and takes a very small value. But if you consider like a integrable case, the OTOC doesn't decay to 0, but it oscillates around 0. So this is the non-universal behavior that I was referring to. So even though OTOCs do not behave exponentially in spin models, spin chains, they still diagnose chaos by having these properties of vanishing at some time scale. That's the part that I skipped. Thank you for this question.
I have, yeah, it's a simple question. So,
Oh, yes.
so one is about in the spin chain, does it have the chaos bound? But the second question is, I mean, what about the chaos bound for flat or digital case?
Okay, good question. Yeah, so in spin chains, you don't get exponential behavior. So you only get exponential behavior if you have some sort of semi-classical limit. So you need some small parameter. So for instance, the small parameter could be h bar or 1/n. So you need some sort of small parameter to get this exponential growth. So in the spin chain, unfortunately, you don't get this Lyapunov exponent. So people define as 0 because the behavior is just not exponential. But that doesn't mean that OTOCs are useless for OTOCs, for spin chains. But you can do something to get Lyapunov exponent for spin chains. You can actually consider, instead of like spin 1/2 operators, you could consider higher representation of SU2. You could consider spin S operators. And if you consider spin S operators and take the limit where S is very large, then you can get a Lyapunov exponent. Basically, because in each point in the chain, you have like large enough matrices. But 1/S in this case would be the small parameter that you need for exponential growth. So now regarding the sitter, I think there is a couple of papers about OTOCs in the sitter. And I think people usually claim that you get the maximal Lyapunov exponent for the sitter as well. But to be honest, I'm not so sure if the situation in the sitter is well understood. I in particular don't have a good understanding of the sitter, so I don't have a good intuition, fortunately.
Okay, thank you.
No problem, yeah. Thank you for your question.
I have a final question.
Yeah, sure.
Could you give some comments on the eigenstate normalization in the holographic setup?
Against heteroization. I better not, sorry. I don't think I know any paper about that. Maybe I'm just not updated in the literature about eigenstate normalization hypothesis. But I know that in the context of quantum mechanics, like, but in holography, I don't think I have seen anything related to that. But maybe it's just my ignorance. I'm sorry for not being able to answer your questions.
Yeah, that's because answer.
Yeah,
Yeah.
So I can say one thing about this larger time scales. Usually OTOCs are like a early time notion of chaos. Larger time scales, for example, I think e to the s, for example, the level space statistics is more important. And people usually talk about a spectral form factor. And yeah, one thing that I forgot to say is that this type of distribution here is what you find in random matrices. So people say that chaotic systems have a random matrix behavior. And this appears in larger time scales. However, this is still much smaller than the Poincare recurrence time. So I'm not familiar with any sort of measure of probe of quantum chaos at such a large time scale. But people usually talk, for this very large time scale, people usually talk about complexity. But unfortunately, I cannot say much about that.
Time is over, so maybe after formal closing, we can discuss. Okay, let's thank again.